In this session, we start with another type of differential equation, namely exact equations. What are exact equations? You observe this equation. dy by dx is equal to 1 by x. Do you feel any strain or stress to solve this equation? No question at all. It is directly y is equal to log mod x plus c, isn't it? This is the right answer. So that differential equation whose solution can be obtained by direct integration can be called an exact equation. Can be called an exact equation. You see, this equation can be dy plus minus 1 by x into dx is equal to 0. Can it be written like that? So it takes the form something into dx plus something into dy is equal to 0, or simply capital M dx plus n dy is equal to 0. One more thing, another equation, look here, dy by dx is equal to y by x. Observe this equation. This can be dy by y is equal to dx by x. Solution of this equation can also be obtained directly by integration itself. You can look at the answer. You can read the answer on this part itself. What is the answer for this? Log mod y is equal to log mod x plus log mod c, or y is equal to cx. Such equations can be called exact equations, and this equation can also be written like this. You can observe this: y dx plus x dy is equal to 0. Again, this takes the form m dx plus n d. Of course, this is a minus sign here, and dy is equal to 0, isn't it? Here m is y and n is minus x. So by observing all such examples, we can come to a particular conclusion that the general or the standard form of an exact equation can be taken as m dx plus n dy is equal to 0. Moreover, for all these examples which we have just discussed, you could have noticed that if the equation is exact, this can be brought to the form m dx plus n dy is equal to 0. Now, can you say the converse? What can you say about the converse? Do you mean that any equation which takes the form m dx plus n dy is equal to 0 is exact? No, need not be. There are certain particular conditions to say or to judge or to take the decision about the nature of m dx plus n dy is equal to 0, whether it is exact or not. Well, now we shall conclude, or rather we shall gather the correct statement regarding the nature of an equation which is exact, like this: an equation m dx plus n dy is equal to 0 is exact if and only if dou m by dou y is equal to dou n by dou x. Dou m by dou y is equal to dou n by dou x. So that is the necessary and sufficient condition, of course, to test whether a given equation of the form m dx plus n dy is equal to 0 is exact. Suppose a problem is given in this form, m dx plus n dy is equal to 0. How to test whether it is exact? You must be able to observe that dou m by dou y is equal to dou n by dou x. Okay, you could have verified that the given equation is exact. Then what about the solution? In the previous discussion itself, we could have got one particular idea. If a particular equation is exact, then its solution can directly be obtained by simple integration or the direct integration. Okay, if a particular given equation is exact, after verifying this condition dou m by dou y is equal to dou n by dou x, we can come to the conclusion that the given equation is exact. I think you might have remembered that. We have decided that a particular given equation is exact. Then what about the solution? The solution is integral m dx plus integral n dy is equal to constant. Of course, some special precautionary measures are to be taken here while obtaining the solution using this formula or this pattern. What are all the precautions? While integrating m, you are supposed to treat y as a constant. Y is treated as a constant. Y is treated as a constant. What y? M is a function of x and y, you see. In m, if at all there are some y's, you are supposed to take that y as a constant. And while integrating n with respect to y, you are supposed to take those terms free of x only. Terms free of x only. By following this condition, you can have the solution directly about that equation, provided that given equation is exact. M dx plus n dy is equal to 0 is exact if and only if dou m by dou y is equal to dou n by dou x. And of course, this is the necessary and the sufficient condition. The most important, the crucial condition that must be satisfied to say whether the given equation is exact or not. Yes. We shall now look at some examples, few examples for this exact differential equations. Consider the equation Consider the equation x cube plus xy square dx plus y cube plus x square y dy is equal to 0. Surely this looks like dou m by dou y. This looks like m dx plus n dy is equal to 0. M dx plus n dy is equal to 0. Well, friend, we may have to get it confirmed whether it is exact or not. You see, m dx plus n dy is equal to 0 has been given. Okay, this is dou m by dou y. What is that? What is dou m by dou y? What is that? Is the partial derivative of m with respect to y. Derivative of x cube is 0. X is a constant. For y square it is 2y. X into 2y is 2xy. And in a similar fashion, you find dou n by dou x. It is an easy matter, of course, to see that dou n by dou x is also 2xy. How and why? Look at that. Derivative of y cube is 0. Y is a constant. For x square it is 2xy. So we should feel happy. This is an exact equation. Okay, friend, one more thing. Here, if you take x as a common factor, you will be having x square plus y square. If you take y as a common factor, y into x square plus y square. If you divide throughout by x square plus y square, this equation can be simplified by x dx plus y dy is equal to 0. Why should we take all this strain and pain Such a doubt you may ask me. You see, you are right, of course. With that idea, you can have the direct solution, of course, x dx plus y dy is equal to 0, or x square plus y square is equal to constant. That will be the answer, of course. See, this method is very, very convenient even if you have x power 4 here. Imagine that situation. If x power 4 is here, if you take x as a common factor, you will be having x cube plus y square here and y cube plus x square there. And the solution in such a case cannot be directly or simply be obtained. Okay, let us follow the procedure first of all. Coming to the point again, let us start from the beginning. This is the given equation. This looks like m dx plus n dy is equal to 0. And we like to test whether this is exact or not. Okay, let us try to get dou m by dou y. What is dou m by dou y? It is 2xy. Absolutely in the similar manner, dou n by dou x. What is dou n by dou x? It is also 2xy. And these are equal. Therefore, the next immediate step is the solution is integral m dx x cube plus xy square dx plus integral n dy, terms free of x only are supposed to consider. So this is y cube dy is equal to constant. Well friend, what is the integral of x cube? X power 4 by 4 plus x square y square by 2 plus y power 4 by 4 is equal to c by 4. I like to take. Why should you take like that? To nullify the denominator, that's all, to cancel the denominator or to adjust the constants. I have taken c by 4 instead of c. Now you multiply the entire equation with 4. What is going to happen? X power 4 plus x square y square, or 2x square y square plus y power 4 is equal to c, or x square plus y square whole square is c, or simply x square plus y square is equal to a constant which is nothing but plus or minus c previously. That is the solution. Well, my dear, we could have made a comment in the very beginning itself, especially for this equation. If you divide the entire equation with x square plus y square, x dx plus y dy is equal to 0 is obtained. And by integrating which we will be arriving at the answer x square plus y square is equal to c. Yes, of course. It's quite simpler. Why should you take this strain? You may ask me a doubt. You are absolutely correct. For such equation, you need not take this pain. If now, I like to change the question. What do you say about this? Even if you take x as a common factor here, x cube plus y square will be obtained here. And if you take y as a common factor there, you will be having y cube plus x square there, isn't it? In such a case, you cannot divide the entire equation by something, and the solution cannot directly be obtained or cannot simply be obtained. At such a situation, this methodology helps us a lot. Now, again for this equation, what is dou m by dou y? 2xy. Dou n by dou x, again 2xy. Hence, this is again exact. The solution now will be, come on, integral m dx, x to the power of 4 plus xy square dx plus, now while integrating m, what is the precaution that must be taken? We could have expressed in forming the solution itself previously in the previous discussion. While integrating m, you are supposed to take y as a constant, and while integrating n, you are supposed to take those terms which are free of x, that is, which do not contain x. Then such term in m is y power 4 only, isn't it? Y power 4 dy is equal to k as a constant. Integral of x power 4 is x power 5 by 5 plus x square y square by 2 plus y power 5 by 5. Now I like to take this k as c by 10. I think you can understand the reason behind that of assuming that k to be c by 10. The only simple and direct reason is 10 is the LCM on the left hand side. That's all. Now you multiply the entire equation with 10. What happens? X to the power of 5 plus 2x square y square plus y to the power of 5 is equal to constant. That gives us the solution. So that is the utility of these exact equations. Yes. If at all a particular equation looks like m dx plus n dy is equal to 0, you try to first of all test whether the given equation is exact or not by using the simple condition. What is the condition? You must be able to find dou m by dou y and dou n by dou x. If you find that those two are equal, then and there itself we conclude that the given equation is exact. And for such an equation, the solution has been given directly, of course. Integral of m dx plus integral of n dy is equal to k. Well, my dear friends, never forget the precautionary measures that must be taken while integrating m and integrating n. What are they? Let us recall, rather let us rebrush our knowledge. While integrating m, you are supposed to consider y as and when it appears as a constant, and while integrating n, you are supposed to take only those terms which are free of x. That's all. That gives you the solution. This is about an exact equation, and the concept will be made clear and firm and concrete only when, if we go through some more examples. We'll be now going to do that. You consider this equation, one more differential equation, which is in the form dy by dx is equal to. If you want to use the concept of an exact equation, you must be able to obtain this equation in the standard form of exact equation. What is the standard form of an exact equation? It is just nothing but m dx plus n dy is equal to 0. Let us now try to get it in that form. You just cross multiply 2x minus y plus 1 dx is equal to x plus 2y plus 1 dy. Am I right? Bring it here. 2x minus y plus 1 dx plus minus x minus 2y minus 1 dy is equal to 0. Now this is in the form m dx plus n dy is equal to 0, isn't it? M dx plus n dy is equal to 0. Well, we may have to test. We need not be satisfied with the just standard form of an exact one. It is the standard form, that's all. We have to believe that it is exact. For that, we may have to test the equation. What is the test? Dou m by dou y. You find it. What is dou m by dou y? For 2x, derivative 0. For minus y, it is minus 1. For 1, it is 0. Hence, this is dou m by dou y is minus 1. Come on, friend. You now find dou n by dou x. What is dou n by dou x? Minus 1. For minus x, it is minus 1. For minus 2y, it is 0. For minus 1, it is 0. Oh, we should feel happy that that given equation is absolutely exact. Why? Because we are happy to observe that both these partial derivatives coincide. That is, dou m by dou y is equal to dou n by dou x. Well, this is exact. Now only one thing remains. So what is that? Obtaining the solution. It is direct. You see, as you could use the concept of exactness here, you are going to have the solution immediately in the next step itself. Otherwise, two more steps are needed. You see, you can solve this in your old methods also, but this is somewhat time-saving method, of course. Now, the solution. What do you say about the solution of this equation? You please notice these steps. I would like to remove these steps because I may save some space. Now we are to write the solution of this equation. You remember the two precautionary measures. While integrating m, you are supposed to take y as a constant, that is 2x minus y plus 1 dx plus n dy. While integrating n, you are supposed to take those terms which do not contain x or free from x. Which are they? Which are all the terms of that sort? Minus 2y minus 1 dy is equal to c. Come on, friend. What is the integral of 2x? X square. What is integral of minus y? It is minus xy. Why? Y is a constant. Minus y is a constant into 1 is x. So it is minus xy, and plus 1 it is x. What is the integral of 2y? It is y square minus y is equal to c. Therefore, the answer is x square minus y square minus xy plus x minus y is equal to c is the direct solution. That is what we say about an exact equation. Well, let us see another example of an exact equation now. The next equation is before us. X plus y dx plus x minus y dy is equal to 0. Well, my dear, there are so many other methods also to get it solved. By taking dy by dx is equal to dy by dx is equal to x plus y by y minus x, and that looks like a homogeneous differential equation. By taking y is equal to vx and by following the usual methodology of a homogeneous format or form, you can solve that. Of course, it is time taking, or some 4 or 5 steps may be required to solve in such a manner. You please observe this equation. This looks like, I think you could have followed my comment. For this equation, you can get it. Dy by dx is equal to y plus x by y minus x. Surely that is homogeneous, you can observe. And by taking y is equal to vx, that is the standard substitution in the standard methodology that is to be applied in the case of a homogeneous equation. There is a way you can solve it. What I mean to say is that is time taking. That is some 5 to 6 steps are needed to solve in that way. Now you observe this equation. This looks like m dx plus n dy is equal to 0. Is equal to 0. This is in the form of an exact equation. But we should not declare that it is exact unless we test it. What is the test that is to be tested? Consider dou m by dou y. What is dou m by dou y? For x it is 0. Why? Because we are having the partial derivative, isn't it? 0 plus 1 is 1. Well, my dear, dou n by dou x, what do you say? For x it is 1, for minus y it is 0. Hence, dou n by dou y is also 1. We should feel happy to declare that the given equation is exact because the condition, the necessary and sufficient condition dou m by dou y is equal to dou n by dou x has been satisfied. Well, we said that it is exact, and we are now ready to have the solution directly within one step. That is the next step. What is it? The solution is, come on, m dx, x plus y dx plus n dy. See, while integrating m, what is the precaution that you have to take? Y must be treated as a constant. And in a similar way, in integrating the part contained in n, you are supposed to take those terms which are free of x, that is which do not containing x, and there is one such term, that is y dy is equal to c. What is the integral of x? X square by 2. What is integral of y? Xy. Why? Because y is a constant. Minus y square by 2 is equal to c by 2. Let me take. Multiply this with 2. What happens? X square plus 2xy minus y square is equal to c. How does it look? It is very simple. The way in which we are able to have the solution is simple, isn't it? Yes. This is the utility of an exact equation. Well, let us now take interest to know some other new words related to exact equation now. Well, follow the steps carefully. As we could just discuss now, we are interested to know a new word. Let me introduce you the word integrating factor. We are interested to know the meaning of integrating factor. Integrating factor. What is the exact and absolute meaning of this word integrating factor? Well, my dear, I would like to explain you the meaning of this word by means of an example only. You consider this equation: x dy minus y dx plus log x dx is equal to 0. Come on, dear, is it exact? You test within a second or 5 seconds. You can test it. What is m? Log x minus y into dx. Log x minus y is m. Dou m by dou y is minus 1. And dou n by dou x is 1. They're not equal. It is not exact. It is not exact. You see, at such a situation, you cannot be in a position to use the solution integral m dx terms with y as a constant and integral n dy terms free of x is equal to c. That type of solution you cannot be in a position to use directly. Then what should you do? There is a simple trick. Look here. You multiply the entire equation with 1 by x square. What happens? X dy minus y dx by x square plus log x by x square dx is equal to 0. Do you believe that this is exact? As of course, without testing dou m by dou y is equal to dou n by dou x is satisfied or not, you will be in a position to say that this is exact. Why? Because you observe this one. It is just nothing but d of y by x plus log x by x square dx. What do you say about the solution? Can that so-called solution be obtained by direct integration or not? Yes, of course. What is the solution which is going to come? Integral of this plus integral of this is equal to constant. What is the integral of this? Y by x plus what is the integral of log x by x square? You can obtain, of course, by using integration by parts. We are not interested in the solution, of course. The thing happening here, you please notice. in the beginning we have noticed that this is not exact. Of course, by multiplying throughout the equation with 1 by x square with a particular function 1 by x square, we are able to see that it is exact. Well, my dear, my question is, how can you declare that this is exact? We have used the meaning of exactness. The solution can directly be obtained by direct integration. That is why it can be noticed that it is exact. I think you could have followed. At this stage, we have not tested this about dou m by dou y and dou n by dou x. But we are able to declare that it is exact because the solution of this equation can be obtained by direct integration. That is why we say that this is exact. The question is, in the beginning it is not exact, but at the last step it is, we have declared that it is exact. What happened in the middle? We have multiplied throughout the equation with 1 by x square. That factor or that simple function with which we multiply a given equation to make it exact is called the integrating factor. That is the integrating factor. In the beginning it is not exact, but of course by multiplying that equation entirely with 1 by x square, and that is observed to be exact. Here, what is the integrating factor? We have used 1 by x square. In short tips to say, the function or the factor with which we multiply a non-exact equation to make it exact can be called the integrating factor. Yes, we like to take interest in the word integrating factor because in the next model of differential equations, that is linear equations, that plays a vital role. Well, my dear, let us observe some more integrating factors in a few examples. We like to witness the selection of an integrating factor in another example. You look here, y dx plus x square y dy is equal to 0. Of course, this has been given directly in the format of an exact equation. And it is our duty, of course, to test whether it is exact or not. Come on, what is dou m by dou y? It is 1. What is dou n by dou x? It is 1 plus 2xy. Surely they are not equal. We have to do something here. What is that something? Previously, we could have had some differentials in our mind, d of xy, d of 1 by xy, d of x square y square, like that. So many things we could have discussed previously. By making use of those differentials, we now try to choose some integrating factor here. You look here, y dx plus x dy plus x square y dy is equal to 0. Okay, y dx plus x dy, now I am multiplying entirely with 1 by x square y square. X square y square plus x square y dy by x square y square is equal to 0. You please note this step in your mind. What has been done? You please notice. We could have multiplied the entire equation with 1 by x square y square. Is this plan successful? Let us see. It will be appeared, of course, at the end of the procedure. Look here. This you can have d of minus 1 by xy. A famous differential, of course, we could have discussed in the beginning itself. What is the derivative of minus 1 by xy? 1 by x square y square into y dx plus x dy. And here x square y square can be cancelled, y by y square is 1 by y. This can directly be had d of log y is equal to 0. Now you must believe that it is exact. Why? Why should you believe? The solution can directly be obtained. The solution can directly be obtained. What is the solution? Minus 1 by xy plus log y is equal to constant, which has been obtained by direct integration. So, there is a particular quantity which has helped us a lot to make this given equation exact. What is that particular factor? 1 by x square y square is the so-called integrating factor in this situation. So, what must be the integrating factor? With what factor? What factor is to be selected so that the given equation can be made exact that can be decided according to the situation and according to the problem. And all the differentials rather d of xy, d of like that, we have discussed a list of such things. So there, those will help us to choose the integrating factor. Here, by keeping this in view only, we could have chosen the integrating factor to be 1 by x square y square. So all these things will help us a lot in finding the solution of a given differential equation directly by direct integration. Yes, well, let us now observe the situations where these integrating factors play a vital role. Yes,